Hello. All right, in this video I'm going to go over basics of kinetic theory. So there's actually 2 pages worth of stuff here. All right, so let's get in. Okay, so the first one is something that we saw in lecture already, but your book only goes over it now. It's the ideal gas law. So remember, an equation, an empirical relation among macroscopic quantities, macroscopic thermodynamic quantities, is called an equation of state. And this is by far the most popular equation of state in thermo, PV equals nRT. So you'll notice I wrote it a couple different ways. So nRT, this is number of moles, n, lowercase n, and then this is the ideal gas, gas constant, 8.31 joules per mole Kelvin. So you multiply by the number of moles of molecules of gas and times the temperature. The absolute temperature has to be in Kelvin. You can't use degrees C or degrees Fahrenheit here. So you're left with a joule. So notice this equation is energy. Energy equals energy. So joules equals joules. So as long as you have pressure in atmospheres, volume in cubic meters, that's a joule, and then the units work out. You might be used to, if you've taken a lot of chemistry, you might be used to the gas constant as 0.0821 liter atmospheres per mole Kelvin. So a liter atmosphere is a bigger unit of energy. You can show that 101 joules approximately is 1 liter atmosphere. So we're mainly going to stick with this one. We're going to be interested in SI units. You can also write PV equals nKT, where capital N is the number of molecules of gas, so a really, really big number, and then times Boltzmann constant, a really, really small number. So a lot of books and a lot of people keep the subscript B, but a lot of times I don't write it. So whether you see it with the subscript or not, the lowercase k is Boltzmann's constant. And notice 8.31 and 1.38. That makes it easier to remember, right? Because they're just forwards and backwards, same number. But you do have to remember the times 10 to the minus 23 for the small thing. That's the gist of that section. For the second section, your book really wants to talk about how fast molecules are moving. So later on, we'll talk about a distribution that gives us more info. But the most important, and from that one, we can drive a lot of different kinds of speed. So like most probable speed is different from average speed, is different from median speed, is different from this thing. From an energy perspective, this is the most important one. This is the most useful one as well. So first, I'm just introducing you to the fact that a lot of equations that we write down can be written on a per molecule basis or on a macroscopic variable sort of basis. So this is square root of 3 kT, so this would be Boltzmann's constant times temperature divided by, and this lowercase m is going to be mass of 1 molecule. Or you could write this on a per mole basis. So basically you can just take this fraction and multiply the top and the denominator here by Avogadro's constant, Na. And that's basically actually what happened with the ideal gas law. If you multiply and divide by Avogadro's number. So lowercase n times Avogadro's number gives you the number of molecules, and then this R divided by Avogadro's number, or divided by 6.02 times 10 to the 23 gives you this thing. So you can also play with your calculator and divide 8.31 divided by Boltzmann's constant in SI units, and you'll get Avogadro's number. Anyway, so what I'm getting at here is that this is the mass of 1 molecule. This is the molar mass, so grams per mole. And actually, if you're using SI units, you have to convert that to kilograms per mole. So plug in, this is the SI unit for the gas constant, and then plug in kilograms per mole for your molar mass in order to get VRMS in meters per second. So VRMS, it stands for the average value of the square of the speeds of the molecules. So if you took every molecule in the room and you squared the speed. Then you took the average of that, and then after that you took the square root. So the way you would read this is go from right to left. So square the velocities, take the mean, and then take the root. RMS, root mean square velocity. Your book, and actually in lecture, we're going to talk about, so classically you could derive this just by considering elastic collisions of molecules against a wall. So defining pressure in terms of, so keeping track of momentum differences, and that's average force on a wall, etc., and then turning that into pressure. A more elegant and useful derivation of this is using something called the Equipartition Theorem. So we'll talk about the Equipartition Theorem soon, right here. The gist of this is that if you look at this right here, so again, you can write this on a per molecule basis or on a macroscopic per mole basis, but notice because I have the lowercase k here, this is per molecule, and so this is the mass of one molecule. What this equation is saying is that the average kinetic energy, so this is like the kinetic energy of one molecule on average, averaged in that special way, root mean square. The kinetic energy of the molecule, of each molecule on average, is this value. So the equipartition theorem says that each degree of freedom accessible to a gas stores on average 1/2 kT of energy. When a gas is free to roam around in 3 dimensions, it's free to move x, y, z direction, and it's storing an amount of energy 1/2 kT in each of those 3 dimensions. So on average, it has this much energy stored in the kinetic energy, just the translational kinetic energy of the molecule moving around. And so you can set up this equation right away, and you can quickly rearrange that to solve for VRMS, and you get this thing, which if you look at this derivation, it takes a lot more time and effort to do that. So the equipartition theorem is actually a really powerful tool that helps us prove a lot of things very quickly. Okay, so I mentioned the equipartition theorem. So molecules store energy for every degree of freedom. And that's the total internal energy or thermal energy. We're going to use those terms interchangeably because we're not talking about chemical bonds or anything. So all of that energy is 1/2 kT times d, the number of degrees of freedom, and that's per molecule. So you would also need to multiply by the total number of molecules to get the total internal energy of the gas, or we're just going to write that as U. Sometimes you'll see it U thermal, U internal, etc. And you might see it without the N. And so again, you have to infer from context, from the equation that you're looking at, are they talking about the whole sample or are they just talking about per molecule? And it looks like because of the capital N, it looks like we're talking about the total energy of the whole system. And just like from PV equals nRT, you can do capital NKT or nRT, right? These should be interchangeable too. So what is the value of D? So D, for the total, if you have a monoatomic gas, so like a noble gas that doesn't bond with another, so for example, helium or argon, it's not going to bond with anything else. And so it's just the molecule, and it can only store energy by moving around, by having translational kinetic energy. There's no other way for it to, it can't rotate. Imagine like a point-like molecule. It can't rotate, and can't vibrate. There's nothing to vibrate. So it only has 3 degrees of freedom. So you would plug in D equals 3 in this equation. Diatomic gases can do more. So oxygen can rotate, in addition to the whole center mass moving in 3 dimensions. At room temperature, these molecules are rotating around, and they can rotate in, around this axis of rotation, or it can rotate around an axis of rotation that's going through the screen. Okay, if the molecule is very small, it's not going to, there's no moment of inertia about this axis, so that one doesn't count. So you get 2 more degrees of freedom for the 2 different axes of rotation that the diatomic molecule can rotate around. So diatomic gases at room temperature, they're storing 60% of their energy in translational kinetic energy and 40% of their energy in rotational kinetic energy. Now, if you look at a plot of degrees of freedom versus temperature for a diatomic molecule, you get D equals 5 for room temperatures. If you cool down your sample really cold, you'll freeze out the rotations. So you can actually make it impossible for this thing to rotate, for molecules to rotate. Or if you keep heating it up, higher and higher temperature, you can actually get it to start vibrating. Get the molecule to start, just vibrating back and forth like that. Now, there's only one axis of vibration, but from a more technical definition of degrees of freedom as quadratic terms in a Lagrangian, you get 2 degrees of freedom for this one axis of rotation. So actually you go up from 5 degrees of freedom to 7 at really high temperatures. So this is really neat because this is the first time in your physics career that you've actually seen quantum mechanics in action. Classically, there's nothing stopping, like, if you can rotate something arbitrarily slowly. There's nothing classically that forbids that. Quantum mechanics says that there's, like, you can try to rotate something, it's not going to rotate at all, but there's a certain amount of minimum energy that it requires to rotate, and then you can maybe have double that amount of energy and rotate it twice as much. It comes in these discrete units. So you're going to learn a lot more about this in Physics 4E and upper division. But this is a consequence of that. So this is like an experimentally determined thing, and later on you can explain it using quantum mechanics. So it's actually really neat. Solids. So if you have atoms all stuck together in some lattice, imagine some 3D lattice here. I can't draw, I think. Yeah, close enough. So you have molecules in 3D. They're not free to move around. There's no translational degrees of freedom. There's no rotational degrees of freedom. But these molecules can vibrate in along 3 different dimensions. And remember, we get 2 degrees of freedom for each of those dimensions that it vibrates along. So actually, solids all have 6 degrees of freedom. And so as applied to, so quickly we're going to get to this equation down here, Cv equals d over 2r. So notice if you plug in d equals 6, you get Cv equals 3r. That's called the law of Dulong and Petit. So if you look at the molar specific heat, which is something we'll talk about in just a second, of solids, they all have the same value on a molar basis. So if you plotted the specific heat of solids per unit mass, it looks kind of random. But if you plot it per mole, you get the same value basically for everything. Okay, so this takes us to specific heat. So first thing, I just want to mention that this is just a repeat of the formula that we already wrote down. So internal energy is degrees of freedom divided by 2 times nRT, and I wrote a delta here, so changes in internal energy and changes in temperature. So I'm assuming that the delta T is small enough that you don't excite different numbers of degrees of freedom when I write this down. Now, this is hinting at what we're going to talk about next week with the first law of thermodynamics. There are 2 things that can change the internal energy, how much energy is stored by a molecule, and that is by heating it up or by doing work on it. So for this week, we're going to assume that no work is done on a molecule. So W is 0, in which case, and that's true as long as the sample, your gas sample, doesn't change its volume. Okay, so this is called molar heat capacity at constant, I wrote down pressure here, but that's bad. This is at constant volume. So let me change that before I forget. So at constant volume, there's no work done, right? The gas isn't expanding or contracting or anything, no work. So all of the energy is kept track of by heat. And heat, if you remember in calorimetry, we have this relationship. Q is, before we had m lowercase c delta T, remember specific heat. We have to be a little bit more careful when we talk about gases because whether we heat something up at constant volume or constant pressure or several different ways, the Q and the delta T relationship is different in all of those different cases. So this is one particular relationship between delta Q and delta T. It's the relationship at constant volume, which is why we have this subscript right here. But the special thing about constant volume, when there's no work involved, is that we can relate this and this, delta Q and delta U. So because of that, and because of our previous relationship, so we can relate delta U here to degrees of freedom. So, looking at this chain of degrees of freedom gives us delta U, gives us delta Q for constant volume, gives us this. We can relate, so if you read this thing from here to here, you can relate D and CV. So the molar heat capacity at constant volume just depends on the number of degrees of freedom. So D over 2 times R. And this is the molar, I put the word molar in parentheses because you might see this instead of R, you could see this times K. D over 2 times Boltzmann constant. And that would be the heat capacity per molecule instead of per mole. Right? So again, it's another one of these instances where you can see basically any of these equations on a per mole basis or on a per particle basis. Okay, so later on, we're going to see delta Q equals NCP delta T. This is the amount of heat involved to raise something at constant pressure, to raise the temperature of something at constant pressure, and CP is different from CV. So this one would not be equal to delta U. Right? But delta U is equal to NCV delta T. So I'm not even going to put this here. We'll worry about that next week. Okay, that was a long section, right? Section 2.3. Section 2.4 introduces the Maxwell-Boltzmann distribution. So this talks about a function, f of v, and the function is the probability per unit speed. So this function satisfies a normalization condition. So the speed of a gas molecule is definitely between 0 and infinity. So this is equal to 1. So our function needs to satisfy this normalization condition, which would allow us to solve for this constant. So I don't really care right now about what that constant is, but we could solve for it, given this formula. What's maybe more interesting here is this dependence. So the v squared times e to the minus. Notice how this is like an energy over energy. And you're going to see this a lot in statistical mechanics. This is like the probability that something happens is like its energy relative to the temperature. So I wrote this in a way that's supposed to be suggestive. So there's two different kinds of energy scales. There's the temperature, KT scale, and then the kinetic energy of the molecule, 1/2 mv squared. And that's exactly the combination that goes in that exponent there. So if you plot it, this function looks like this. And yeah, so on your homework, you're going to do a lot with this. And we give you some tricks, some hints with how to do integrals of functions like this. So you're going to explore this would be the most probable speed. This is at the very peak of that distribution, right? That's the most probable one. But the average of all the speeds is a different value from that. So the average is farther out here, and then VRMS is even farther out there. So you get to compute a whole bunch of stuff related to that. Okay, I think that was my quick introduction to all of the main equations from this chapter. So you might have a few more equations to learn for your homework, or that you'll see in lecture this week, but these are the main ones that you'll need for your homework. All right.